3. So, reminder about a couple of things. Probability. Any probability has to be between 0 and 1, including 0 or 1. And the sum of all probabilities of the simple events has to add up to 1. It doesn't add up to 1, or it gets more or less, it's not a probability distribution. As far as the mean and variance and standard deviation, that's just a weighted average. Another name for the mean, besides weighted average here, would be expected value. That's important. What do we expect to happen on average in the long run? And the variance is where we take the deviations, distance from the mean of any particular observation, we square it, and we multiply by its probability, which is again weighting it, very important. Adding all of those up, that gives us the variance. If we take the square root of that, that gives us the standard deviation of the probability distribution. Now here I have probability distribution drawn to look normal relatively. And the idea, page 205 in the book, I hope you read this repeatedly, this is super important. The success of the rest of the quarter depends on it. Unusual values. X is considered unusually large, like maybe the probability of having 6 or 7 out of 7 girls. If the probability of that happening or higher, that's what this says right here, the tail on the right, if that probability is less than 5%. Okay. Sometimes we'll even say or equal to. Is the 5% fixed? No. Some situations we want it to be less than that. Something can be unusually small, like the probability of being 3 feet tall in the United States. We'll find that less than 5% of the population is less than 3 feet tall. So that would be an unusual measurement in that context. And again, unusual values are things that mark a tail, and that tail and all the probabilities in there add up to something less than 0.5. All the probabilities in this right tail add up to less than 0.5. If that's the case, then the particular number we're talking about that marks that boundary, right, that's like a percentile. So here we're talking about the 5th percentile, here we're talking about the 95th percentile. Those numbers mark what it means to be unusually large or unusually small. All right, other things. That's general for any kind of probability distribution. My pen just died. There we go. Binomial probabilities, Bernoulli trials. So the book illustrates this a little bit different than I do. You need to read that to double check the difference. They have 4 things to check off. I have 3. We're repeating some kind of situation. That's what they call number 1. And the situation is basically the same every time. And the result is either a success or a failure. The probability of a success, which we call P, is the same for each trial, and the trials are independent. Okay? Those are very important conditions. If we meet those conditions, then we have what are called Bernoulli trials, and that leads to a binomial distribution. Calculation of any probability for an individual measurement in a binomial distribution is this formula right here, by hand. On the TI 80-somethings, 82s, 83s, 84s, maybe even other 80s, it's the number of trials, n, p is the probability of a success, x is the particular number we're trying to find, and that is binomial PDF. There's also a binomial CDF, which gives you a left-hand tail. So note on the TIs, binomial CDF, same parameters, n, number of trials, p, probability of success, x, particular number we're talking about, that gives you a left tail of probabilities. So in other words, that gives you the probability, let's make this a capital X to distinguish, of finding any number that is less than or equal to the number we're looking at. And that is a left-hand tail. So if this were our binomial distribution right there, and this is our number big X, we are talking about this whole probability instead of a single column in a histogram. I believe that's a histogram. If you're going to use a spreadsheet, whether it's a Google spreadsheet or Excel or OpenOffice, then the command is binomial distribution, the x value we're thinking about, number of trials, probability, and then true or false. True for cumulative, meaning tail, and false for PDF, meaning a single column, a single number in that distribution. All right, so let's take a look at some ideas from the homework. So here are some questions about what constitutes a binomial distribution. So let's look at number 5, for example. Treating 863 subjects with Lipitor and recording whether there is a yes response when they are asked if they experienced a headache based on data from Pfizer. So if the data from Pfizer indicated that a certain percentage of people that take this are responsive to it and that they would do a yes, like maybe it's 60%, then we could say this might be a binomial distribution. Other thing, when we randomly select one of these, if we then take them out, then we've ditched the independence idea because we're not replacing them back in there. So this could be a situation with independence. It could be a situation also where it's not a fixed probability because we really don't know the probability yet. So depending on whether we're replacing these people or not, if we don't replace a person we selected, then it is definitely not binomial because it's no longer independent trials. Let's take a look at number 7, gender selection. Treating 152 couples with the Y-sort gender selection method developed by the Genetics and IVF Institute and recording the ages of the parents. Ages, there's a lot of different numbers that could be. That's not a success or a failure, so it's definitely not binomial. 8, treating 152 couples with the Y-sort gender selection method, blah, 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 and recording the gender of each of the babies. Okay, so maybe if we consider gender like females is a success and male is a failure, then that's good. If when we grab one of these 152 people, if we don't replace them back into the sample, then we lost independence. So here we might argue that we're going to grab somebody and then we have 151 people left, changing the denominator of our probabilities, in which case we don't have independence. So that's probably not either. Let's try another one. How about New Yorkers? 500 different New York City voters are randomly selected from the population of registered voters and asked if he or she is a Democrat. Okay, so Democrat's a success, and we know the probability roughly of being a Democrat in New York City. If we pull one person out of 2.8 million, we might argue that we still have independence there because 1 out of 2,800,000, that losing that person isn't a big deal. So one might argue that that is a binomial distribution, and we could certainly approximate it with one. So that's a possibility there. All right, let's do a problem we have to calculate. All right, and let's find a cute problem down here. The above are just calculations. Can you get your calculator to do the right thing? Let's jump down here. Now here, they are generating a binomial distribution for us, and they're saying the probability of a success here is 45%. So let's see, here's the Minitab table. I can make this table for you on a spreadsheet in a moment. P is 45. We want to know when blood donors are randomly selected, 45% of them had blood that is group O. We want to the display shows the probability is obtained by entering the values n equals 5. So what we're doing is we're randomly selecting 5 people, and we want to know what's the probability that some number of them have group O. So let's look at number 26 here. Copy that into my sketchbook here. Screen clip. And we'll grab that table too. Oh, slow down there. All right, let's reproduce that table in my spreadsheet. So I have my Google Docs open here, binomial distributions. And in this one, I'm looking at a binomial distribution where I have 10 trials. I need to back that up to 5 trials. Come on, baby, you can load. It's thinking about it. The computer appears to be stressed by all the different things opened. Okay, so I'm going to change this. I'm going to make probability of a success. Come on, success. There we go. Oops, try that again. Equal to 0.45. And computer is struggling. Here we go. And the graph should shift. Graph shift. Definitely stressing my computer. There we go. Okay, now that's for 10 trials. So I need to redo this to go for 5 trials. So we'll just adjust the formula here from 10 to 5 and fill it down. And ignore the results. Actually, I'll just delete them for now. About this. Lose some stuff. Maybe just killed my computer. Oh shit! Oh dear. I mean, oops. Excuse me. Darn. Oh, there we go. We got rid of some of them. Let's get rid of the rest. Okay, my probabilities add up to 1. There's my binomial distribution. And what we should see is that those probabilities match the ones given in the book. Let's copy them in just to make sure. Insert screen clipping. Okay, so you can see I've got a few more decimal places than the book does, but this is the same data, same calculations. And to do that, I had to enter this command right here, binomial distribution, x, n, p, and false, because I wanted PDF, not CDF. I didn't want tails, I wanted each column. All right, so then we need to answer a question. What's the probability that at least 3? At least 3. So if I have at least $3, that means I have 3 or more, right? So that means I want to add up having, oops, that's the highlighter, 3, 4, or 5. So I want to add up these numbers right there. And I can ask the computer to do that for me if it's not too slow. Now that's kind of the opposite of a cumulative, so I'll do that in 2 different ways. From a cumulative gives left tails, not right tails. So here, if I ask 2 equals sum these numbers above, that's the probability that I want. And I get a probability of 0.4-ish. Let's say we can call it 0.407, so 40.7%. And it threw an extra thing because of my thing isn't well designed. That's all right. So I get approximately 40%. About 40% of the people in this group, about 40% of the time will find that 3 or more people out of 5 have type O blood. So again, we just calculated the probability that X is greater than or equal to 3. And we got that as about 40.7%. So what does that mean? It means that if the probability that any one individual has a 45% chance of being group O, then, and we grab 5 people randomly at a time, the probability that 3 of the 5 are group O is 40.7%. All right, now check this out. Let's use a different color. This group of numbers right there, those are the probability that X is less than or equal to 2. Now that's a left tail. if I take 1 minus that left-hand tail, the probability that x is less than or equal to 2, that will give me the remaining 3 numbers, right? Because these are complements of each other, the yellow group and the blue group. So I'm going to check with the TI about this. I'm going to do a CDF to get a left tail. I'm going to do 1 minus that left tail. So 1 minus second VAERS to get the distribution value, scrolling down to get the binomial cumulative distribution. Oops, too far. On mine, it's option B. And then here I want to enter number of trials, probability, and what is the particular x value we're stopping at. Okay. So number of trials is 5, comma, probability of a success is 0.45, comma, and we are going all the way up to 2. So we're removing the from 100%, we're removing the probability that x is 0, 1, or 2, which leaves 3, 4, and 5, which is what I want. So if I hit enter, that should give me that 40.6-ish percent, 0.7. Right? So there's multiple ways to calculate these guys, depending on what tools you're using. You need to get used to your tools. Let's do another one, and then we'll play around with the mean. So let's see, where the heck is the homework? There she is. Let's jump to the next page. What would I do? All right, let's see. How about affirmative action, maybe? All right, affirmative action. Researchers conduct, number 35, a study to determine whether there were significant difference in graduation rates between medical students admitted through special programs such as affirmative action and medical students admitted through regular admissions criteria. And it was found that the graduation rate was 94% for medical students admitted through special programs. This is based on data from the Journal of the American Medical Association. So a probability of a success that they graduated was 94% if they were in one of these special programs. If 10 of the students from the special programs are randomly selected, we want to find the probability that at least 9 of them graduated. Okay, at least 9. So if I have at least $9, that means I could have 9 or more. So we want the probability that 9 or 10 of them graduated. Okay. So I'm going to draw a little picture of that. All right, so I've got some kind of distribution. This is number 35 in section 5.3. So let's say this is my distribution. That's not really what it looks like. And this is 9. I want 9 or more. Okay. So on the calculator, this one, the white stuff over here, let's say that right there. This is 8 right there, would be the probability that x is less than or equal to 8, which would be the binomial CDF of 10, 0.94, oops, 8. I want the complement of that. Excuse me a second. Give me 1 minute. So I want 1 minus that probability. So let's grab the calculator, and we're going to go 1 minus the binomial, which is option B for me, CDF. So I'm going to eliminate probability 0 through 8, which leaves only 9 and 10. And there are 10 trials. Probability of success is 0.94. And I want to eliminate up to 8. Enter. So that is probability is, ooh, look, that's a big one. Let's write that down, 0.882. So the probability that x is greater than or equal to 9, so at least 9, is 88.2%. Very high probability. And the questions, let's go back. We want to define the probability at least 9 of them graduate. Okay, so at least 9 out of the 10 graduate, that's an 88.2% chance if there's a 94% chance that any one of them will graduate. Would it be unusual to randomly select 10 students and get that only 7 of them graduate? Okay, so that means they want 7 or less. Okay, so that is, if we draw a picture of that, for part B, let's say 7 is right here. So we want to know what is the probability down here. So let's get back and double check that we're answering the right question. Would it be unusual to randomly select 10 students from the special programs and get only 7? And so only 7 means we're applying that kind of low. Only 7 graduated. Wow, that's not very high. You know what I'm saying there? That would be the binomial CDF of 10.94, 7. So let's ask. It's a left-hand tail, so we don't have to do the 1 minus there. Okay, binomial CDF, 10, 0.94, 7. And we should find that's relatively small, but is it small enough? Ooh, yeah, we get about 1.9%. So we would say, yes, this is an unusually low number. Graduation rates. We expect more than 7 to graduate. 9 or more is 88%, right? All right, I'm going to come back with another recording doing some more problems from 5.4 and talking about normal distributions. Ta-ta for now.